Hello and welcome to this video on how to interpret latent profile analysis results. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate methods including factor analysis, structural equation modeling, and latent class analysis and latent profile analysis. If this is something that interests you, then please consider subscribing to this channel. Also, don't forget to check out the description for additional resources, including courses that I teach for QuantFish. And I actually offer an introduction to mixture modeling with Mplus course for free that you can find in the description, where I show you how you can estimate models such as latent profile models in the Mplus software. Here in this video, I want to focus on the interpretation of latent profile analysis output. Perhaps you have already estimated your first latent profile analysis in R or in Mplus, but now you're stuck and you don't know what to look for in the output. Especially the Mplus output for a latent profile analysis is pretty long and has a lot of information, and so it's sometimes difficult to know what to look for. And so I want to walk you through the key pieces of the output here that you should pay attention to, whether it be an Mplus output or an R output for a latent profile analysis, so that you can understand better what we use for the interpretation of the analysis in latent profile analysis. So before we do that, what is latent profile analysis? So let's talk briefly about what this analysis is all about. And I have a separate video here on this channel in which I deal with that question in more detail. So you can check out that video as well, which has exactly this title, What is Latent Profile Analysis? So just real quick, with latent profile analysis, we address population heterogeneity. So the idea is that we have a mixture of different subpopulations that we're trying to identify, where we're trying to unmix our heterogeneous population into homogeneous subgroups. So it's like the idea of cluster analysis, where we're trying to find groups of individuals that are similar in terms of a set of variables that we have their scores for. And so it is a little bit similar to factor analysis in that we are using a set of indicators or observed variables. So here, for example, the scale scores from a personality test or personality questionnaire, the big five. So we would have a sum score here, for example, for emotional stability, extraversion, openness, agreeableness, and conscientiousness. And we're using these observed scores as indicators of latent classes. And of importance in latent profile analysis, these indicator variables are continuous, or are assumed to be continuous at least. So they are metrical variables, test sum score variables, or questionnaire sum score variables that are on an interval scale level. And so the idea here is that the relationships or the covariances between those observed variables are accounted for by a latent class variable, so by a categorical latent variable that represents, in this case, the personality type, where individuals might differ qualitatively in terms of their profiles of means across this set of indicator variables, and potentially also the classes might differ in their variances and covariance structure. And so the idea here is that we're introducing a categorical latent variable to explain the associations between the continuous observed variables, and the question is, how many classes do we need? So do we need 2 classes or 3 classes or 4 classes? How many classes are needed to sufficiently account for the covariances between those indicator variables? And that's one question when we interpret the output, is about model fit and about how many classes we need. So it's similar to factor analysis, for example, or especially exploratory factor analysis, when we want to find out how many factors do we need. And so here we're not classifying variables by finding the correct number of factors, but instead we're classifying individuals by trying to find the right number of classes. And so that's the whole idea behind latent profile analysis, is to cluster individuals and to unmix a heterogeneous population and identify those subgroups that are homogeneous, and then potentially one goal could be also to classify individuals according to their most likely latent profile or latent class membership. More broadly, latent profile analysis is part of the broader statistical modeling class of mixture models or mixture distribution models, like, for example, classical latent class analysis, like factor mixture models, regression mixture models, growth mixture models. All these types of models aim to find or identify population heterogeneity and then identify homogeneous subgroups. In contrast to classical latent class analysis, which uses categorical indicator variables, for example, binary or ordinal variables, latent profile analysis uses continuous indicators. So what are we looking for in the output? This video is about interpretation. So how do we interpret the results? And in order to understand that, we need to first of all understand what the parameters are in a latent profile analysis model. And for that, I'm showing you the model equation here of a latent profile model, where you can see on the left-hand side the distribution of a set of observed scores given model parameters. So the yi vector here is our vector of observed variables, where we have the big 5 in this case, so 5 variables, and the theta here indicates a set of model parameters. And then on the right hand side you have the model parameters. And so first of all, we have a gamma C parameter here, which indicates the class size of a given class C. So we have up to uppercase or capital C classes, and so each class has a proportion. So each class has a size that we estimate. So that's one type of model parameter that gets estimated in latent profile analysis, is the unconditional probability of belonging to class C. And so those class sizes across the C classes sum up to 1.0, because individuals are in one and only one latent class. So the classes have to sum up to 100%, so to say, the class size parameters, which means that you have only C minus 1 independent proportion parameters. The last proportion is fixed. So when you have, for example, 3 classes and you know 2 class proportions, then you know the third as well, because they have to add up to 1.0. And then next are the parameters that are related to the nature of the classes. So what the classes actually look like, how they are interpreted. And so that's to say the class-specific distribution here with class-specific means mu c and a class-specific covariance matrix sigma c. So the means here are of key interest in a latent profile analysis, the class-specific means, because they tell us whether somebody, for example, in a given class is high on openness, high on extroversion, high on whatever, or low. And so that's how we interpret the profiles later on, is based on these class-specific means. And so each indicator variable, each of the big 5, gets an estimated class-specific mean in each latent class, and then based on those class-specific means, we can then plot our profiles. And that's, so say, the key thing in the interpretation of a latent profile analysis, is what those mean profiles look like. In addition, we could also model the variance-covariance structure based on the sigma c. So the sigma c is the class-specific covariance matrix, where the variances of the indicator variables are in the diagonal, and off diagonal we have the covariances between the indicator variables, and those could also vary between classes. Now, oftentimes we specify a latent profile analysis model with a restricted variance-covariance structure, where the variances are set equal across classes and the covariances are fixed to 0. That's the default parameterization, for example, in the Mplus software, so that the focus is exclusively on differences between the means between classes. And so then the variance-covariance structure really isn't of much interest. When the variances are set equal across classes and the covariances are all fixed to 0, then really we would focus on the interpretation of the means. However, this need not be the only specification possible, and it's not necessarily the most realistic specification either, because variances might differ between the classes, and you can free up that constraint of equal variances across classes in Mplus and other programs. So you don't have to assume that. You can even assume that there are within class covariances, which may or may not make sense. But so in summary, what are the key parameters that are relevant for us for the interpretation of the output are those proportion parameters that tell us something about the class sizes, and then the means, the mu-c parameters that tell us something about the class-specific profiles of means. So let's take a look at those in more detail. But before we do that, we actually have to determine model fit. So remember that one goal of at least exploratory latent profile analysis is to find out how many classes we need. And that's not part of the model equation, so to say. It's not a model parameter that gets estimated where the data tell you, oh, this is, so say, you need 3 classes or you need 4 classes, but instead we are determining that based on model fit statistics. So it's again similar to what we do in exploratory factor analysis, where we compare the fit of different models with different types of criteria, for example with chi-square statistics or chi-square difference tests, or with a parallel analysis that looks at eigenvalues and so on. And so in the same way we would do that in latent profile analysis. Typically we would estimate a 2-class model, 3-class model, 4-class model, 5-class model, and then compare the fit of those. And so one common approach is to look at information criteria, which programs like Mplus output by default. For example, the Bayesian information criterion BIC is often used. And so those scores have no absolute meaning for a given model, but they are useful to compare different models. So we can compare this BIC value here for this solution to a solution with a different number of classes and look for the solution that has the smallest BIC value, for example, to determine the number of classes. And then you could also plot the BIC values like in a scree plot, and then look at where the minimum is and determine the number of classes that way. Another approach is to look at a likelihood ratio difference test, and more specifically a bootstrapped likelihood ratio difference test with a parametric bootstrap procedure that determines the p-value appropriately for comparing different numbers of classes. In this example, 2 classes were compared against 3 classes. The 2-class model here is the model under the null hypothesis. And you can see that the likelihood ratio difference here, 153, or 2 times the log likelihood ratio difference, which gives us a likelihood ratio statistic, is significant according to this bootstrap p-value that is very, very small based on 1000 bootstrap samples, and that means that the 2-class model is rejected. So the null hypothesis that the 2-class model is the true model can be rejected because this p-value is significant, or in other words, the 3-class model fits significantly better than the 2-class model. So that's important for the interpretation here in terms of model fit. Next, we would take a look at 3 classes versus 4 classes, and we would compare the BIC values there. We would compare, or we would look at the parametric bootstrap likelihood ratio test and see if 4 classes are still better, fit better than 3 classes, and then we would stop once we find that there's a non-significant chi-square difference here for the comparison of models with different numbers of classes. So in this case, we would prefer the 3-class model over the 2-class model because this is highly statistically significant. In addition, we also can look at classification accuracy. And so that tells us something about how well individuals are classified based on our latent profile model. And so one thing that, for example, Mplus outputs is the entropy. The entropy is a summary measure of classification accuracy. It varies between 0 and 1, and so values closer to 1 indicate better overall classification quality. It's not such a good measure really for model selection, and oftentimes models with not so great entropy values can still be acceptable. What I like to look at more, what I think is more interpretable and tells me more, are the specific average latent class probabilities for the most likely latent class membership. So those ones tell me, for example, if somebody who had, or on average, we should say, if those people who were assigned to class 1 based on their most likely class membership, what probability they had on average for that class. And so you can see in this case, for class 1, those individuals who had the highest probability for that class on average had a probability of 0.908 for this class, which is high. So they had an over 90% chance of belonging to this class on average. So that's good. For class 2, it was a little bit lower, 0.793. So on average, they had only an about 0.8 chance of belonging to this class, and there was some overlap with class 3 and class 2. So with class 1 and class 3. So there is not, the separation here is not as good. Class 3 has a probability average of 0.88, so that's also pretty high, indicating that those individuals were also clearly classified on average. So that's a good way to assess classification quality of your model. When those diagonal probabilities are rather low, it would mean there's a high degree of uncertainty about where to put individuals, and then that may be an indication that the model is not so great. It's not such a great model for unmixing your population appropriately. Next are the actual LPA model parameters. And first, remember we discussed the gamma C parameter, which gives us the class size in terms of a probability or proportion parameter. And those are given in Mplus under final class counts and proportions for the latent classes based on the estimated model. So you can see in this example, 3 classes were extracted, and first we get the estimated number of individuals in each class based on our sample size. So in this case, there were about 700 cases, or over 700 cases here. And so about 266 individuals would be in class 1, about 207 in class 2, and about 280 in class 3. Now, in terms of the actual proportions, gamma C, that would mean that the class size of class 1 was about 35%, class 2 was about 27%, and class 3 was about 37%. Notice that these add up to 1, so only 2 of these are independent model parameters. The last one is fixed, so to say. Once you know the first 2, the last one is a given, because they have to add up to 1 by definition, because there's no partial class membership. Everybody has to belong to one and only one latent class in latent profile analysis. So those are ones that you would definitely report when you report the results of your latent profile analysis. You would want to make sure that you give those class proportion parameters gamma C, because they tell us about the prevalence of each class. Now, for the actual interpretation of the classes, we focus on the class-specific means, which are here shown only for latent class 1, because otherwise they wouldn't all fit very well here onto this slide. And so I'm only showing this for class 1, but we get these for each class. So you can see here the means for emotional stability, extraversion, openness, agreeableness, conscientiousness. And so here in this class, the means here were between 5.4 and 3.0. And of course, this doesn't tell us anything unless we look at the other classes as well. So really, we wouldn't know, is that a lot? Is that not a lot? It's relative to what the other classes look like. And the best way to interpret that or to be able to interpret that appropriately is by plotting the means. And that's where this name or term latent profile analysis comes from. from the profile plot, so to say, where we plot those class-specific means. And so here this is shown for a 3-class solution for the 5 indicators: emotional stability, extraversion, openness, agreeableness, and conscientiousness. You can see on the y-axis you have the class-specific means. And here are the means in the first class, which has high means on all 5 big 5 indicators. Those individuals are referred to as resilients in the literature on personality profiles. They are high, they're low on neuroticism and high on emotional stability, high on extraversion, high on openness, high on agreeableness, and high on conscientiousness. Next are the so-called over-controllers, which have lower scores on emotional stability, lower scores on extraversion, openness, and also lower scores on agreeableness and conscientiousness. And then finally, we have under-controllers that are in the middle with regard to emotional stability, extraversion, and openness, and that are particularly low on agreeableness and conscientiousness. And so based on these profiles of means, we interpret the profiles. That's to say what tells us what these classes are like and whether there are qualitative differences between them or only quantitative differences, where we would, for example, only have a low, medium, high profile. Or in this case, it's more complex, where we have some profiles that have that crisscross here. That makes it more interesting than when we have only low, medium, and high profile. So typically we're looking for a solution where some of these profiles crisscross, because then that indicates that there are some interesting qualitative differences potentially between the profiles. So this is what you would look at. The key output here: model fit statistics, class sizes, and the profiles in terms of the class-specific means. Those are the key things to look for in a latent profile analysis. I hope you found this video useful to learn more about how to interpret latent profile analysis results. If you did, then please consider subscribing to this channel, and don't forget to check out the description for additional resources. And I'll see you next time.